On a cold November night, two faint glimmers appeared on the digital display of a small Italian observatory. At first glance, they seemed unremarkable, just another pair of pixels in the endless sea of stars. But as the astronomers adjusted their instruments, a quiet realization began to ripple through the room. These weren't ordinary reflections of light. These were the newest images of the interstellar object now known as 3I Atlas. And what they revealed might have rewritten everything we thought we knew about comets, and possibly about life itself. For months, telescopes around the world had been tracking Atlas as it drifted closer to the inner solar system. It was expected to behave like any other comet, to shed dust and gas, to blaze a long, luminous tail as solar radiation scorched its icy surface. Yet when the Virtual Telescope Project released these images, something was wrong. Or rather, something was missing. There was no tail, no bright coma of vaporized ice, no signature plume that marks every known comet in our history. Just a compact, unwavering point of light. Cold, sharp, almost deliberate. Scientists looked again, ran the data twice, and then a third time. The images from July taken by the Hubble Space Telescope matched perfectly. No change in structure, no visible decay, no scattering debris. In every measurable way, Atlas had remained unchanged. Silent, steady, indifferent to the heat of the sun that should have torn it apart. It shouldn't be possible. For an object estimated to have lost billions of tons of material, the absence of a dust cloud was like watching a volcano erupt with no smoke. The math didn't add up. The physics didn't add up. And as Harvard astrophysicist Avi Loeb quietly noted, for an object of this mass and proximity to remain this pristine, that's inexplicable. For the scientific community, this was more than a curiosity. It was a fracture in understanding, a whisper that something in the cosmos wasn't obeying the familiar rules. And so the question emerged, steady and unsettling, echoing in labs, observatories, and late-night discussions across the world. If this isn't a comet, then what exactly is moving through our solar system? The Virtual Telescope Project, founded in Italy by astrophysicist Gianluca Massi, has spent years peering into the night sky, offering the world a bridge between professional astronomy and public wonder. From its quiet domes nestled in the countryside, this small network of robotic telescopes has streamed live images of eclipses, asteroid flybys, and distant comets, giving humanity a window into the infinite. But on November 5th, 2025, its lenses captured something far more consequential. In the vast silence of space, a solitary object, known as 3I Atlas, was behaving in ways that no natural body ever should. To understand the significance of this moment, we must look back to the brief but astonishing history of interstellar visitors. Until just a few years ago, humanity had never directly observed an object entering our solar system from the depths of another star system. That changed in October 2017 when astronomers at the University of Hawaii spotted a faint cigar-shaped object passing through our cosmic neighborhood. It was named Oumuamua, Hawaiian for a messenger from afar, arriving first. Its shape, its tumbling motion, and its inexplicable acceleration sparked one of the most profound scientific debates of our time. Was it a fragment of an alien world or something built? The mystery was never solved. Then came Borisov, discovered in 2019, a true comet this time, its icy tail shimmering as it plunged toward the sun. Unlike Oumuamua, Borisov behaved predictably. It vented gas, glowed brightly, and then disintegrated as expected. It reminded scientists that even interstellar travelers could follow the laws of physics we understood, but 3I Atlas would break that fragile comfort. Larger, heavier, and slower to fade than either Oumuamua or Borisov, it carried with it a quiet defiance. Every calculation, every expectation drawn from centuries of cometary behavior failed to explain what astronomers were seeing, or rather what they weren't seeing. As it approached the inner solar system, NASA's Jet Propulsion Laboratory charted its trajectory with precision. The European Space Agency's ground observatories tracked its faint light signature, while Harvard's Center for Astrophysics began running simulations. Each agency, each observatory, anticipated the same thing: that Atlas would behave like a comet nearing the sun. It should have brightened dramatically, trailed a magnificent coma of vaporized ice and dust, and then slowly faded after perihelion, the point of closest approach. But it didn't. Instead, it stayed immaculate, smooth, silent. On October 29th, at the very moment it should have begun venting gas, 3I Atlas did something deeply strange. It accelerated, not a sudden burst, but a subtle, persistent push, an acceleration unaccounted for by gravity alone. NASA's data showed that the object had deviated by 4 arcseconds from its expected position. To most, that figure sounds trivial, but in the precision-bound world of orbital mechanics, it was enormous, equivalent to drifting nearly 80,000 kilometers off course in a matter of weeks. Such deviations can happen naturally, but only when massive jets of gas push against a comet's surface as ice sublimates into vapor. This outgassing acts like miniature rocket engines, producing small but measurable thrust. The problem was that no outgassing could be seen. No tail, no vapor, no plume. By all accounts, something invisible was pushing 3I Atlas. Harvard astrophysicist Avi Loeb, who had led much of the early research into Oumuamua, called attention to the math. For an object with a mass estimated at over 30 billion tons, maintaining that acceleration through outgassing would require losing over 5 billion tons of material in a single month. An eruption bright enough to be visible across the solar system. And yet, the telescope saw nothing. For scientists trained to see the cosmos as a set of predictable equations, this was deeply unsettling. The sun's gravitational pull is one of the most precisely understood forces in nature. Objects that stray from its grip always do so for reasons we can measure, but Atlas seemed to be rewriting that certainty in real time. At NASA's Jet Propulsion Laboratory in Pasadena, researchers ran models again and again. Each iteration failed to explain the readings. At the European Space Agency, teams cross-referenced every variable: solar wind, thermal emission, radiation pressure, magnetic influence, but none could produce the kind of consistent push Atlas was showing. And at Harvard, the question began to circulate in hushed tones. If it isn't outgassing, then what is it? The world's leading observatories turned their eyes toward December. That was when Atlas would make its closest pass to Earth, about 167 million miles away, just enough for the Hubble and James Webb telescopes to peer directly into its halo. The expectation was clear: if Atlas was venting gas, we'd see the evidence then. If not, the conversation about what we were truly observing would change forever. In the meantime, the silence surrounding the object grew louder. Each night, telescopes gathered more data, and each morning, scientists woke to the same contradiction. A comet that refused to act like one. A visitor from the stars that ignored every rule of motion and matter we thought we understood. For now, the only certainty was uncertainty. The universe had delivered a puzzle wrapped in perfect calm, gliding silently through the void, and humanity could only watch, waiting for the next revelation. In celestial mechanics, there are very few surprises left. Every orbit, every trajectory, every slow spiral through the dark is governed by forces we have come to understand with exquisite precision. Gravity, the universal sculptor, dictates nearly everything that moves. When a comet swings toward the sun, we can calculate its speed, its curve, and even its fate with mathematical elegance. But every now and then, something arrives that makes even the most confident equations tremble. 3I Atlas is one of those somethings. To understand why, we have to begin with the idea of non-gravitational acceleration. In essence, it means an object is moving in a way that gravity alone cannot explain. Every comet experiences it to some degree. When the sun heats up a comet's surface, ice buried deep within begins to vaporize. The resulting jets of gas act like miniature thrusters, nudging the comet off its expected path. It's small but measurable. We can predict it, we can see it, and we can correct for it. But with 3i Atlas, those same physical principles stop making sense. NASA's Jet Propulsion Laboratory detected a deviation of about 4 arcseconds from Atlas's expected orbit. That sounds microscopic, but in cosmic terms it's staggering. Tens of thousands of kilometers off from where the laws of gravity said it should be. Harvard's Avi Loeb ran the numbers. The object, he calculated, has a mass of roughly 33 billion tons, far larger than either of the previous interstellar visitors, Oumuamua or Borisov. Yet despite this enormous weight, it's accelerating at 0.02 millimeters per second squared, a faint but persistent push. Those two numbers, taken together, lead to a single unavoidable conclusion. If this acceleration were caused by natural outgassing, 3i Atlas would have had to shed at least 5.5 billion tons of material in just 1 month. To put that in perspective, that's the equivalent of an entire mountain evaporating into space, silently, invisibly, without leaving a single trace of vapor or dust behind. Imagine standing at the foot of Mount Everest and watching it burn away into nothing, yet seeing no smoke, no flame, no glow, only the empty sky where it once stood. That is the scale of the paradox facing scientists right now. In theory, the natural explanation is simple. Comets are dirty snowballs, frozen relics from the early solar system made mostly of water, carbon dioxide, ammonia, and dust. As they near the sun, the ice vaporizes, producing the familiar coma and tail that stretch for millions of kilometers. That vaporized material reflects sunlight, which is why comets glow so brightly. The outflowing gas also acts like rocket exhaust, creating the small non-gravitational acceleration we observe. Every comet we've ever tracked behaves this way, everyone except Atlas. To visualize the difference, consider two cosmic travelers captured in the same images from the Virtual Telescope project. One is Comet Lemon, a typical comet of our solar system. It's alive with energy, its tail streaming away from the sun, its core surrounded by a bright, luminous haze of ionized gases. The physics here are beautifully consistent. Solar radiation hits the comet, the heat releases gas and dust, and that material scatters light back toward us. Lemon behaves exactly as textbooks predict. Then, beside it in the same field of view sits 3i Atlas, a single compact point of light, sharp, unwavering, pristine, no tail, no glow, no haze, nothing to indicate it's shedding billions of tons of matter into space. It looks more like a small, solid asteroid than an active comet racing through solar heat. And yet, its motion insists otherwise. It's being pushed. But by what? Some scientists initially suspected measurement error. Perhaps the acceleration was an illusion, an artifact of imperfect observation, or of assumptions built into orbital models. But those doubts quickly faded. Multiple independent observatories confirmed the same result. The data came from different telescopes, different instruments, and different tracking software, yet all showed the same anomaly. The European Space Agency verified the deviation with its own astrometric readings. NASA's JPL recalculated the orbit with refined algorithms and still found the same non-gravitational component. The margin of error wasn't enough to explain it away. The next idea was radiation pressure, the gentle force exerted by sunlight itself. For extremely small or thin objects like dust or debris, sunlight can indeed cause acceleration. But for something as massive as 3i Atlas, radiation pressure would be negligible, far too weak to produce the observed effect. That explanation, too, was discarded, which left only one natural mechanism: outgassing. But that, too, fails under scrutiny. Even the faintest level of mass loss required to produce the observed acceleration would generate a brilliant, unmistakable cloud of gas visible to telescopes across the globe. The Hubble Space Telescope, capable of detecting vapor densities 1,000 times weaker than what would be required, saw nothing. The James Webb Space Telescope, designed to detect faint infrared signatures of gas and dust, also found no trace of ejected material. Every instrument that looked saw the same thing: an object that should be venting like a geyser but appeared perfectly dormant. In physics, when observation and theory collide, it's the observation that wins. And yet, the absence of evidence here is itself the most puzzling evidence of all. A comet accelerating without visible thrust is like a ship sailing across the ocean without wind, without waves, and without a motor, moving somehow through sheer impossibility. The implications are vast. If this acceleration isn't caused by natural processes, then either we are witnessing a new kind of cometary physics never before observed, or we are seeing something that was deliberately engineered. But in science, speculation comes last. For now, all astronomers can say with certainty is that Atlas is defying every known model. The data remain consistent, the numbers remain solid, the silence remains absolute. 3I Atlas drifts onward, hundreds of millions of kilometers from the Sun, its trajectory bending ever so slightly under an invisible force. Every telescope that watches it sees the same serene defiance of the laws that govern motion. Every scientist who studies it confronts the same uncomfortable truth. Something is pushing 3I Atlas, but nothing visible is doing the pushing. The deeper scientists looked into the data, the stranger 3I Atlas became. What began as a single unexplained acceleration soon unfolded into a tapestry of contradictions, each defying the fundamental expectations of celestial mechanics. In the long tradition of astronomy, mysteries often fade under better instruments and clearer data. Yet, with every new observation, Atlas only grew more unexplainable. What follows are the 9 anomalies that now define it, 9 defiant signatures carved into the silence of interstellar space. The first anomaly is its impossible path. Every planet in our solar system orbits on nearly the same flat plane, a cosmic tabletop known as the ecliptic. Most comets, asteroids, and interstellar fragments approach from random directions in space, their inclinations scattered like dice thrown across that table. The odds of an interstellar object aligning almost perfectly with the ecliptic are incredibly low, less than 0.2%. Yet 3I Atlas arrived traveling along that very plane, as though it had deliberately aimed for the same thin sheet of space where every major planet moves. Imagine a billiard table surrounded by darkness, the planets rolling in graceful circles upon it. Then, from far beyond the room, another ball is thrown, and by some miracle of precision it lands perfectly level on the table's surface, rolling beside the others as if it had always belonged there. To those who study celestial motion, that precision feels unnatural. It is the difference between chance and choice, between a random arrival and a plotted trajectory. The second anomaly deepens the confusion. During the summer months of 2025, when Atlas neared its perihelion, telescopes observed something never before seen in the behavior of comets: a jet of material erupting toward the Sun. The physics of cometary tails are among the oldest understood in astronomy. Solar radiation and the solar wind push dust and gas outward, away from the Sun, like a breeze blowing smoke from a fire. Every known comet obeys this rule, yet Atlas defied it completely. Its faint emission appeared directed inward, as if it were resisting the very force that governs every particle of dust in the solar system. Scientists likened it to a person running against a strong wind and watching their hair stream forward instead of back. Radiation pressure should have pushed any particles away, not toward the heat source. To produce a jet in that direction would require an internal mechanism capable of counteracting solar forces, a phenomenon entirely inconsistent with nature as we know it. Then comes the third anomaly, its sheer scale and velocity. Interstellar objects are expected to be small fragments, pieces flung from other systems during their violent formation. They move fast, but their mass limits how much energy they can carry. 3I Atlas breaks that balance. With a mass estimated at over 30 billion tons, it is vast, larger by orders of magnitude than Oumuamua or Borisov. Yet it still cuts through the void at tremendous speed, faster than smaller bodies that should, by all logic, outpace it. Imagine a freight train overtaking race cars on a straight track. In every dynamic model, size and speed work against each other. Large objects retain gravity longer, escaping their parent systems more slowly. For Atlas to achieve its current trajectory, the ejection energy must have been immense, beyond what natural planetary collisions or stellar tides typically produce. The numbers suggest either a cataclysm on a scale we have never witnessed, or a propulsion method entirely outside our current understanding. The fourth anomaly lies not in its motion, but in its timing. From the moment it entered our solar system, Atlas seemed to thread a sequence of encounters too precise to be accidental. It passed near Mars, then Venus, then Jupiter, each within a narrow window that allowed observation but offered little insight. And during its most revealing moment, its closest approach to the Sun, it slipped behind our star from Earth's perspective, rendering it nearly invisible to ground-based telescopes. It was as if it had plotted a path through the solar system designed to avoid direct scrutiny. Astronomers describe the alignment as uncanny. To pass near three major worlds, yet evade detection from the one planet most capable of observing it, is the cosmic equivalent of a traveler visiting every major city in a country, but somehow bypassing all the security cameras at the main airport. When its orbit was traced backward, the geometry appeared perfect. The probability of such alignment by chance was astronomically small. It passed every major world but left us blind. Anomaly 5 opened a new kind of puzzle, the question of composition. When scientists examined the light reflected from Atlas through spectral analysis, the ratios were startling. The object's surface contained far more nickel than iron, a proportion rarely found in natural comets. On Earth, such metallic consistency is not the product of geology but metallurgy, processes that refine raw material into specific, engineered alloys. To see that ratio replicated in a supposed comet was like finding the chemical signature of stainless steel inside a mountain of ice. Natural objects tend to be chaotic mixtures of elements, a cosmic soup of randomness. But Atlas's spectrum was too orderly, too specific. As one researcher described it, it's as if someone melted asteroids together and then polished the result. Whether that meant a natural process unknown to us or something constructed remains open. But either way, the composition of 3I Atlas refuses to belong to nature as we understand it. The sixth anomaly cuts even deeper. Comets are called dirty snowballs for a reason. They are mostly ice, ancient reservoirs of frozen water and gas. The models predict 80 to 90% water content for typical comets, but Atlas contains only around 4%. In essence, it is dry, drier than the Sahara, drier than any body ever observed in the outer system. This dryness makes it more like a metallic asteroid than an icy wanderer. Scientists propose that perhaps it had lost its volatiles long ago, burned away during a previous stellar encounter. But even the oldest comets from our own Oort cloud retain traces of ice beneath their crusts. To find one this parched suggests an origin far stranger than simple age. It may have been exposed to unimaginable heat, or perhaps it was never icy at all. Its dryness erases the very definition of what a comet is supposed to be, hinting that we might be looking at an entirely different category of object, one that was built, not born. The seventh anomaly lies in the light it reflects. When polarized light from Atlas was analyzed, the results didn't match any known natural body. Polarization describes the direction in which light waves vibrate, a unique signature that depends on the texture, composition, and structure of a surface. Every kind of surface, rock, ice, dust, gas, produces a distinctive polarization pattern, like a fingerprint of light. But Atlas's fingerprint doesn't exist in any known catalog. It doesn't resemble that of Borisov, Oumuamua, or any comet ever studied. The pattern implies a surface that scatters light in a way that cannot be explained by dust or crystalline ice. Some suggested microstructures or complex reflective materials. Others proposed highly ordered metallic grains. Whatever it is, it reflects light in a manner that nature doesn't seem to favor. In essence, it shines with a kind of precision, as if the light were being intentionally directed rather than passively scattered. The eighth anomaly stretches across time itself, reaching back nearly half a century. In August of 1977, a radio telescope in Ohio recorded a narrow band signal from deep space, a burst that lasted 72 seconds and then vanished forever. The astronomer who found it scrawled one word in the data margins: "Wow." For decades, the "wow" signal remained one of the most tantalizing events in the history of SETI, a sound from the void that seemed to come from nowhere and never repeated. When the trajectory of 3I Atlas was mapped backward through space, scientists noticed something extraordinary. The direction it entered from, the very coordinates on the celestial sphere, matched the approximate region from which the "wow" signal had been detected. The alignment is not perfect, but it is striking, like two arrows shot from opposite ends of time landing near the same target. No one claims causation, but the coincidence deepens the sense that this is not random. Two events, separated by nearly 50 years, both point to the same corner of the galaxy, as if some quiet story has been unfolding in the dark all along. And finally, the ninth anomaly, perhaps the most dramatic of them all. As 3I Atlas neared its closest approach to the Sun, astronomers noticed its spectral color shift toward blue. This was unexpected. Cold objects reflect red light more easily, while hot objects emit or scatter blue. The Sun's surface temperature is about 5,800 degrees Kelvin, and yet Atlas appeared to reflect light as if it were even hotter. The data implied either a surface of ionized gases energized by internal processes, or a reflective material engineered to scatter shorter wavelengths. In both cases, it contradicts natural expectations. A comet this cold should glow dimly red, not radiant blue. If it were emitting light through internal energy, it would suggest a power source hotter than the Sun itself. That possibility remains unverified, but even in its simplest interpretation, the spectral data describes something profoundly alien to ordinary cometary matter. It is as though the object possesses its own quiet furnace, a light that does not come from reflected sunlight but from within. Whatever it is, it glows with the color of power we cannot yet replicate. Each anomaly alone might have been explained away as coincidence, error, or the limits of instrumentation. Together, they form a pattern that resists every conventional interpretation. The story of 3I Atlas is no longer a simple cometary mystery. It is a riddle written in physics, motion, and light. And as it drifts through the solar system, indifferent to our questions, it leaves behind the haunting impression that we are watching something both ancient and new. Something that does not merely visit the Sun, but understands it. Throughout the history of science, humanity has wrestled with a single uncomfortable truth. Sometimes nature refuses to fit neatly inside our equations. The story of 3I Atlas is not just about a comet or a fragment of rock from beyond the stars. It is about how we respond when the universe hands us something that refuses to make sense. Science is built on skepticism, but skepticism has two edges. It protects us from fantasy, but it can also blind us to discovery. Every major leap in understanding, from heliocentrism to relativity, began as an anomaly someone refused to ignore. For centuries, the scientific method has been our most powerful tool. Observe, measure, predict, and verify. But it also depends on something more fragile: humility. When evidence challenges our theories, it's human nature to defend what we already believe. Yet progress demands that we confront those contradictions head-on. 3I Atlas sits precisely in that uncomfortable space, the crossroads where data and dogma collide. Its acceleration, its brightness, its silence, all these should have been explained by now. And yet they remain unresolved, suspended between physics and mystery. Harvard astrophysicist Avi Loeb, one of the few who first dared to suggest that Oumuamua might not be entirely natural, has spoken often about this resistance. His message is not one of certainty, but of intellectual courage. Loeb argues that when data fails to fit our models, the data must take precedence. To dismiss an observation because it doesn't match theory, he once wrote, is the opposite of science. In his view, the cosmos is not obligated to conform to our expectations. It is our duty to expand our understanding to meet it. This principle is not new. It echoes through every revolution of thought that once shook human confidence. When Galileo turned his telescope toward Jupiter in 1610 and saw moons orbiting another world, the discovery shattered the belief that all motion revolved around Earth. The establishment tried to suppress the finding, not because it lacked evidence, but because it defied certainty. When Copernicus placed the sun at the center of the system, his model was dismissed as heresy. Centuries later, Einstein's theory of relativity faced ridicule before time itself proved him right. And even in our own era, new ideas, especially those that flirt with the possibility of technology or intelligence beyond Earth, often meet that same quiet resistance. Yet the lesson remains: reality does not ask for our permission before revealing itself. It simply waits for us to be ready to see. Perhaps that is why 3i Atlas feels like more than an object. It feels like a mirror held up to our own limitations. For every data point we gather, we confront another reminder that our grasp of the universe is partial, our understanding incomplete. In its silence, there is a kind of reflection, a reminder of how small we still are in a cosmos that rarely explains itself. There is an emotional solitude in this kind of discovery. The scientists watching Atlas each night are not adventurers gazing through telescopes in awe. They are questioners staring into the unknown, waiting for the universe to answer with either confirmation or contradiction. They know that the difference between wonder and fear often comes down to interpretation. A single measurement could mean the difference between a comet and a machine, between nature's randomness and intent, between isolation and the realization that we may not be alone. And so, the world waits. Between December 19th and late January, 3i Atlas will reach its closest point to Earth, just over 167 million miles away. The Hubble Space Telescope, the James Webb, and countless observatories across the globe are preparing to record its every flicker, every spectrum, every hint of vapor or light. If the object behaves like a natural comet, it will brighten, vent gas, and display the tail that has eluded observers for months. If it remains unchanged, silent, and pristine, the implications will ripple through every field of astrophysics. It will not just rewrite a chapter of science, it will reopen a question we thought had been settled. Are we truly alone in this vast, indifferent universe, or have we already been visited by something that defies our categories entirely? This is the tension of our age, the intersection of humility and hubris, of data and disbelief. The next few months will test not only our technology, but our willingness to accept what it reveals. Because if 3i Atlas continues to defy every model, every equation, and every expectation, then this December, humanity might face its most humbling question yet. Telescopes are ready, sensors are calibrated, and the sky waits. Across mountaintops and deserts, in orbit and in darkness, humanity's instruments stand pointed toward the same invisible coordinate, a small, silent traveler moving against the backdrop of eternity. In the next few weeks, 3i Atlas will make its closest approach to Earth, passing at a distance of roughly 167 million miles. It is close enough for our most powerful eyes to trace its every shimmer, but still far enough to remain beyond touch, beyond certainty, beyond reach. The anticipation carries a strange stillness. At observatories from Chile to Hawaii, from the Canary Islands to space-based platforms above our atmosphere, teams have prepared for months. Computer models are running day and night, predicting light curves, plotting spectral ranges, and estimating reflectivity. Each photon that arrives from Atlas will be dissected and compared against every known class of natural body: asteroids, comets, metallic fragments, carbon-rich dust. And yet, beneath the technical precision lies something unspoken: the awareness that no simulation may be enough. The universe has a way of humbling even our best predictions. We learned that from Oumuamua, from Borisov, from countless cosmic surprises that refuse to fit our patterns. But Atlas feels different. Its silence feels deliberate, its behavior too composed. The data are clean, the acceleration consistent, the light unchanging. It behaves less like a tumbling relic and more like something under control. That may be coincidence. Or it may be something else entirely. Could it be artificial? The question is whispered more often now, no longer confined to fringe speculation. A growing number of astrophysicists admit that they cannot dismiss the possibility outright. If a civilization advanced enough to cross interstellar distances exists, would its technology resemble our expectations? Perhaps not. Perhaps what we see as a comet's stillness is simply the efficiency of design, a machine built to endure the deep, unrelenting cold between stars. A probe that doesn't emit, doesn't flare, doesn't signal, but simply drifts, patiently, purposefully, until its purpose is fulfilled. There are other possibilities, equally wondrous, equally unsettling. Maybe Atlas is a remnant, a derelict fragment from a civilization that has long since perished. A silent messenger wandering through the void, carrying the physics and metallurgy of minds we will never know. Or perhaps it's something more abstract, a natural formation shaped by forces we have yet to describe, a window into a new branch of celestial mechanics, waiting to teach us that our current understanding of motion and light is still incomplete. Whatever it is, its arrival has already altered us. It has forced scientists, philosophers, and ordinary people alike to confront a simple but profound realization that our neighborhood in the universe is not as empty as we once imagined. The sky is no longer a closed system. It is a highway of visitors, a corridor of movement. In less than a decade, we have witnessed not one but 3 travelers from beyond our star's reach. And if 3 have come, there may be hundreds more. On December 19th, the countdown begins in earnest. The Hubble Space Telescope will capture high-resolution imagery at multiple wavelengths. The James Webb Space Telescope will study its thermal profile, searching for even the faintest trace of vapor or infrared emission. Ground-based observatories will track its polarization, measuring how its surface reflects and bends light. The data will pour in slowly, pixel by pixel, photon by photon, a language the universe speaks only to those patient enough to listen. For the astronomers who will sit through those long nights of observation, this moment carries both excitement and a kind of reverence. They know that discovery often comes not with fireworks, but with silence, with a subtle pattern hidden inside numbers. Somewhere in that data may lie the first undeniable clue that 3i Atlas is unlike anything we've ever encountered. Or perhaps it will reveal that our fascination was misplaced, that it is, after all, just an unusually stubborn piece of cosmic rock. But even that outcome carries meaning, because whether Atlas proves extraordinary or ordinary, it will have served its purpose, to remind us how much we still do not know. It has reignited a sense of curiosity that modern science sometimes forgets, a willingness to look up, to question, to wonder. It has reminded us that the unknown is not something to fear, but something to approach with humility. As the object continues on its path toward Jupiter in March 2026, its trajectory will take it farther from the sun, its brightness fading once more into the background glow of stars. By then, the data will have been collected, analyzed, and debated. Papers will be written, arguments will be made. The mystery may deepen, or it may dissolve. But the experience of confronting that mystery, the collective breath humanity takes when faced with something it cannot explain, will linger. In the grand timeline of the cosmos, our observation window is nothing more than a blink. For a few brief weeks, we have the privilege of watching something ancient glide through our system, indifferent to our questions, yet unavoidably tied to our curiosity. It does not know we exist. It does not care. And still, its presence stirs something deeply human, a desire to understand, to connect, to make sense of the infinite. If 3i Atlas is indeed a machine, then it carries a message from intelligence beyond our comprehension. If it is natural, then it is proof that nature herself still holds surprises beyond imagination. Either way, it is a teacher, and the lesson is the same: humility. We are students standing at the edge of a cosmic classroom, gazing at a phenomenon that may redefine our place in the universe. The final nights before its closest approach will be filled with tension, not the dramatic kind, but the quiet, reverent kind. The feeling that accompanies moments of truth. Telescopes will stare into the dark, data will stream across fiber lines, and scientists will wait, knowing that whatever they find will echo far beyond their screens. And then, as the weeks pass, and the light of Three Eye Atlas begins to fade into the black sea of interstellar space, we will be left with silence once more. A silence heavy with unanswered questions, rich with meaning, and alive with the promise that this will not be the last time the stars surprise us. Somewhere beyond the thin silence of interstellar space, Three Eye Atlas drifts, silent, steady, indifferent, carrying with it an answer we may not yet be ready to understand.